Alright, so in the previous lecture we proved the 5-list coloring theorem of Carsten-Thomason. Now let me go back to the vertex coloring and edge coloring. So here's the theorem that we know, right? So chromatic number is at most 4 if graph is planar. Now let me tell you something about complexity of determining chromatic number at most k, right? So somebody give you the graph and you have to decide whether or not the chromatic number is at most k. Can you do it efficiently? Does there exist a polynomial time algorithm to decide whether the chromatic number is at most k? So the chromatic number is at most 2. This is same as bipartite. Right. So you can easily see that it's in the intersection of MP intersection co-MP, because if I want to convince somebody that chromatic number is at most 2, I can find the coloring, right? Coloring with the 2 colors. If I want to convince somebody that chromatic number is bigger than 2, I just need to find an odd cycle, right? If I have an odd cycle, then chromatic number is at 2 and bigger than 2. Otherwise, I don't have a chromatic number bigger than 2. And this is a common conjecture that MP intersection co-MP is equal to P. So from this observation, we can already guess that this could be probably polynomial time solvable, and which is the case. If you look at the proof of this this characterization, the graph has chromatic number at most 2 if and only if it has no odd cycle. If you look at the proof, it is actually algorithmic, and it gives you an algorithm. Now, how about deciding chromatic number at most 3? Can you have a really nice characterizations in terms of something like an odd cycle? And the answer is no. Actually, we don't have any good description of graphs of chromatic number at most 3 that can be checkable in polynomial time. No, let me say it this way. We don't have any good certificate to say that chromatic number is bigger than 3. We do have a good certificate to say that chromatic number is at most 3. That's why it's in MP. But it's not co-MP, because we don't have a good certificate, right? Good certificate means it's like it is a polynomial size compared to the input size, and one can verify the claim by checking this certificate. All right, so, and it turns out that deciding this problem is MP complete, even if G is planar. What does that mean? That means if I give you a planar graph and we ask, is the chromatic number at most 3? Then that problem is actually quite hard. It's very hard in such a way that any other NP hard problems can be solved. No, any other NP problems can be solved if you can solve this chromatic number problem. And there are many difficult problems like Hamiltonian cycles or coloring. Coloring was one of the typical problems. SAT problems, set problems. But anyway, what you can remember is, from 3, we don't have good characterizations. If you do have a good characterizations, then you do solve this famous conjecture that P is equal to MP. So it's funny, because what's funny is asking whether chromatic number is at most 4 for planar graph is an easy problem because of 4-color theorem. Why? Because you can just answer yes all the time. Right? Because if you restrict the input graph to have a input graph to be planar, then deciding whether chromatic number is at most 4 is easy, and actually Robertson-Seymour Sanders-Thomas algorithm will give a quadratic time algorithm. I mean, their proof in 1995 gives a quadratic time algorithm. So given a planar graph, you can actually color them. The original proof of Appel and Haken also gives a polynomial time algorithm, and running time is, as far as I remember, it was n to the 4, where n is the number of vertices. All right. How about this Brooks theorem? No, Beijing's theorem. Right? You have seen that chromatic number is at most delta plus 1 if G is simple. No, edge chromatic number is at most delta plus 1 if graph is simple. And now, if we ask whether or not edge chromatic number is at most delta, actually it turns out that this is already NP hard. So asking whether a graph, simple graph, has edge chromatic number at most delta is only, I mean, you only reduce 1 and this extra 1, and that's already NP hard, even if graph is planar and has degree 3. So this is very strange, right? I mean, you have us a very simple situations. Oh, maybe I should change my words. Yeah, so right, I shouldn't say that, right? So I'm sure that the this edge chromatic number is this deciding whether it's at most delta is NP-hard, but if graph is planar and the maximum degree is 3, there is an easier solution. We will talk about that later. If graph is bipartite, then this is easy because of Koenig's theorem, right? Koenig's theorem tells you that edge chromatic number is delta. So that's funny because anyway, what's happening is this number is always delta or delta plus 1. So we have really precise range. I mean, almost precise, right? You can determine maximum degree easily just by looking at the degree sequence, and yet it is difficult to decide which of these two values is the correct answer. Now, let me tell you the conjecture. So here's a least coloring conjecture. Now we go back to the least coloring. This conjecture says that okay, let me tell you this way. So the okay, what is this? I didn't define it yet. So this is least edge chromatic number. So what is least edge chromatic number, or sometimes called the least chromatic index? Okay, so what is that? That is, I mean, now instead of giving list of colors to every vertex, as we did in the previous definition of, right? Yeah, list coloring. On the left hand side, you see that the list assignment is to map each vertex to a set of colors. Instead, here you give a list of colors to every edge, and then graph is L list color L. Well, what is it? L list colorable if you can choose color for every edge, so that the JSON edges get different colors. And then list chromatic index or list edge chromatic number is the minimum case such that you can find the coloring for all possible list assignment of size and list k at each vertex. Okay. Here it doesn't matter whether or not I replace this by inequality. So, and this is still a conjecture. It's a still open problem. You're welcome to prove it. The reason why it's striking is that this side and both sides are difficult, and we don't even know whether this number is delta or delta plus 1. Right? So we don't have a good characterization of this, we don't have a good characterization of that. So I expect that this will be a difficult problem. And one inequality is trivial, right? This inequality is trivial. So normally for vertex coloring, list chromatic number could be arbitrarily bigger than the chromatic number, right? Because, for instance, complete bipartite graphs. We've seen that K33 has chromatic number 2 and list chromatic number 3. And this gap could be big if you grow the size. But here, when you go to the edge version, they are going to be equal. That's the conjecture. We don't have any count example yet. There may be a count example. Another way of defining this list chromatic index as the chromatic index of the line graph. You remember the line graph, right? So vertices are the edges of the graph, and the two vertices are the JSON if the corresponding edges in G are the JSON. Now, what we're going to show you is this theorem due to Galvin in 1995, which proves that for a simple bipartite graph G, these two are equal. And why bipartite graphs? Because when you have a bipartite graph, edge chromatic number is equal to the maximum degree, so the right at least the right hand side is easy. So we can expect that something easy can happen. Okay, so that's Galvin's theorem, and the actual statement of Galvin's theorem is for all bipartite graphs, not just for simple graphs, but for the simplicity of the course. And for this course, we're gonna only cover the simple case. All right. Now, I'm gonna show you a very useful lemma, which will be used to prove the Galvin's theorem. Now, here's a graph. So let G be a graph, and let D be an orientation. So which means that you made a direction for every edge of G, such that every induced subgraph of D has a kernel. So what is a kernel? Kernel is kernel of a directed graph D is a set of vertices. Okay, let me say stable set. Do you remember the definition of stable set? Stable set means that no two vertices are adjacent. Okay, let me just stable set. Oops, it's stable set U of vertices such that every vertex outside of U has has an out neighbor in U. So you have a vertex U such that no two vertices inside U are adjacent to each other. That's first condition, stable. And every vertex outside has at least one out neighbor. That's the second condition. So you have to satisfy two conditions. Then it is called a kernel. And so that's the definition. Then for any list assignment L of G with LV at least DEGV plus 1. So what is degree plus? So this is the number of outgoing edges from V. So meaning that it's out, and so this is called the out degree. Number of outgoing edges from V, right? So if you have a vertex V, then you look at these. In a directed graph, you have incoming edges and outgoing edges, and the number of outgoing edges is called the degree of, it's called the out degree. So whenever you have a list assignment where each vertex has more colors available than its out degree at D, we prove that G has an L list coloring. So that's the lemma. So okay, how do we prove that? This is a simple induction. Okay, so we choose let alpha be a color appearing in LV for some V. So choose one color and let X be the set of vertices so that alpha is contained. Before the proof, we fixed the list assignment L satisfying this property, right? The number of colors at V is at least out degree it's larger than the out degree. Now, if you look at the G bracket X, so induced subgraphs, Okay, so D, let's look at D bracket X. So the sub, this must have a corner. Why? Because in the lemma, it assumed that every induced subgraph of D has a corner, and dx is an induced subgraph, so it has a corner. So you have G, and then you have X, right? These are vertices having alpha in this list of colors, and then there is a U, right? Which is a stable set, so that every vertex outside U in X has our neighbor. Now, what we do is we define L prime of V. Okay, let's not use same V. Let prime of W to be LW if W is not in X, right? Outside, nothing changes, and LW minus alpha if W is in X minus U. Okay, now what we're gonna do is we apply induction on D minus U. And what happens? Every vertex in X minus U lost one out neighbor because of the definition of a kernel. Every vertex here has at least one out neighbor. When you delete U, you lost one out neighbor, so the out degree is decreased by 1. So even if I delete the color alpha, you still satisfy this condition. Okay, so therefore D minus U has an L prime list coloring C. Okay, I should say G minus U, right? So that means I can color every vertex outside of U properly from the list L prime, and L prime never uses alpha. Right. Now we extend that coloring to an L list coloring by coloring vertices of U with alpha, right? So that's it. Okay. Right, so we color this vertex, this set by alpha, and remaining we apply induction. So this is for vertex list coloring. Now we're going to use this to prove Galvin's theorem. Okay. Now, so let delta be the delta G, right? And we knew by Koenig's theorem, we knew that chromatic index is equal to delta because it's bipartite. So it's enough to prove that the least chromatic index is at most delta. So okay. That's right. Now let xy bipartition of G, right? Let C be a delta edge coloring of G. We knew that there exists a delta edge coloring because of Koenig's theorem, right? Now, what we want to do is to find an orientation of the line graph of G. Find the orientation of line graph of G such that every induced subgraph has a corner. Okay? And furthermore, the size of list is this. Alright, so that's, we want to apply lemma. So how do we orient, right? So E and F. Actually, it was initially bipartite graph. Right? So this side is X, this side is Y. Right. So we have this, we use color C to orient edges of the line graph. We orient arrow of G so that you put E to F if C of E is bigger than C of F and EF meet at X, or C of E is less than C of F and EF meet at Y. Okay, so what does that mean? Like, let me give you an example. Right, this is X, this is Y. So let's say this is color 1, 2, 3, 1, 3. Right? So what is the line graph? So the line graph is like you have a vertex 2, right? I'm using these vertices to be here, and oh no, it's not vertices. So the edges are becoming vertices. Right, now what we're gonna orient is, like, for instance here, C color of this is bigger than color of that, so E to F, so this to 1, right? So 2 to 1 and 3 to 2 and 3 to 1. So that's orientation on the left hand side when they meet at X, and when they meet at Y, then it's the opposite, right? So the smaller one to bigger one. So C, the 1 to bigger, 2 to 3. So that's orientation. Now, let's look at the out degree. How many out degree do we have? Right? If I have an edge here, degree plus in this orientation, how many edges does it have? So here is a, let's say this color is C of E. Then on the left hand side, if they meet X, then the out neighbors are the colored by the color which is less than C, so it's a CE minus 1 many out degrees, out neighbors. On the right hand side, you have the delta colors and the CE, right? So this many out neighbors coming from here because those are the number of colors bigger than CE. So when you add them together, so total number is less than CE minus 1 plus delta minus CE. So it's delta minus 1. So that means since we have a list assignment, I should say actually, let L, did I say that? Let L be a list assignment. For line graph of G such that L of E is at least delta for actually equal to delta for all E of the edges of graph G, then obviously L of E is at least out degree plus 1 for all E, right? So that's good enough for us, right? So what does that mean? That means at least we satisfy this condition that every list has at each edge, at each vertex of the line graph, each list has size bigger than the out degree in the orientation. So that satisfies at least one condition here. Well, how about kernel? Why does every induced subgraph of D has a kernel? So what is here? Now we use this theorem. Remember that. Note that G has a stable matching. We claim, okay. Let's say let U be the subset of VG, and then we need to prove that D bracket U. Yeah, okay, let me go back. I need to prove that and I need to prove that every induced subgraph of D has a kernel, right? Now, so what is induced subgraph? It's same as deleting vertices of the line graph. Deleting vertices of the line graph is same as deleting edges of the graph G, right? So, enough to show that D has a kernel. Because everything is symmetric, so I don't have to. Even if you have an induced subgraph, you can think of it as a my graph. But anyway, let me not say that. So let U be the vertex set, and let H be the subgraph of G induced by U. Having U as edge set. Subgraph of G whose set of edges is U. Now, we know that since H is bipartite, H is a stable matching under any, for the preference given by the orientation of the, what does that mean? That means, right, so you have a vertex in X, and this vertex prefers to have a smaller color, okay, because it's oriented, when we set this orientation, we want to make orientation like this. If this is 2, 1, right? So that means X would prefer this edge instead of that. All right. However, for vertex in Y, that would prefer smaller number. Right? If I have an edge colored 4, and then in its out neighbor, if it has 2, then, oh no, the other way around. If this is 1, Y actually prefers larger number. Okay, under this preference, you have a stable matching M. We claim that M is a kernel of the induced on U. Why? Okay, why is this the case? I need to look at the people outside of the outside of matching, right? So let's say this is my M. Now, if I have an edge like this, do I have at least one out neighbor? If I do have an out neighbor, no, if I don't have any out neighbor in M, what does that mean? That means it's not stable, because both of these vertices will be happy to add it into matching, and they are happier, right? So both ends will be happier by adding this edge in the matching, so that means this matching is not stable. If I have an edge like this, and if it has no out neighbor to M, that means actually the person here is actually prefer this blue edge, and the person here is rather to be married than single, so it's still unstable. How about the other case, like if I have an edge like this, if it doesn't have any out neighbor, then this prefers that, this prefers that, right? So still it's the same as definition of stable matching, right? So that means this is actually just follows from the definition. So maybe I don't have to say it. Then M is just kernel. And this proves that G, line graph of G is L list colorable. Okay, so that's the proof. All right, our next topic is about perfect graphs. The name sounds weird because you normally don't want to say something is perfect. Well, why is it perfect? What graphs are perfect? Okay, to do that, I will explain the chromatic number and clique number. I mean, chromatic number, we know what it is, right? But clique number, is maximum size of a clique in G. So what is a clique? Clique is a set of pairwise adjacent vertices. Right? So if you have a clique, you make a complete graph out of it, right? So it's a set of vertices, not a graph. So it's, I mean, if you have a stable set, then when you take a complement of the graph, you have a clique. And it's easy to see that if you have a clique, if the clique number is k, then chromatic number is at least k. Why? If the clique number k means you have k vertices pairwise adjacent. And all these vertices should get distinct colors. So chromatic number should be at least k. Therefore, we can see that chromatic number is always bigger than or equal to clique number. But this gap could be arbitrary. Actually, it was a theorem of Erdős that there is a graph having large chromatic number and no short cycles. I wrote it in a very imprecise way. More precisely, for K and L, there is a graph of chromatic number bigger than K, and as G has such that it has no cycle of length and most L, right? So you don't have any short cycles and your chromatic number is big. So this means that if you look at the locally, I mean, you pick a vertex and look at the graphs of distance hundreds from this vertex, and everything looks like a tree because you don't have a cycle of length. Let's say you don't have a cycle of length million. Then if you look at the neighborhood of size like 500,000, it still looks like a tree. You cannot find any cycles. So locally, it looks like a chromatic number is 2, because trees have chromatic number 2. But however, this theorem of Erdős says that chromatic number could be arbitrarily big, bigger than any number that you describe. Okay, so that means in particular there is a graph which has no triangles, and yet chromatic number is huge. So that means the clique number is, there's a graph clique number 2, but this is like very large. So it is possible so that this gap between omega and chi could be arbitrarily large. But sometimes chromatic number is equal to clique number. So we may try to characterize graphs whose chromatic number is equal to the clique number. But this goal is not easy because you might have an arbitrary graph. Okay, so let's say you have a graph on 100 vertices. And the chromatic number could be completely different from the clique number. Now I attach complete graph on 200 vertices. Let's say this is my graph G. So it is disjoint union of these two graphs. So you have components. One component is K200, the other component is arbitrary graph of small size. And chromatic number of this graph is 200, because any graph on 100 vertices is 100 colorable, so the chromatic number is just 200. Clique number is 200 because there's a complete graph on 200 vertices, nothing bigger. So in this case, chromatic number is 200 and clique number is 200. And yet, we don't see any good structure except there's a complete graph on 200 vertices in somewhere. That just means omega is 200, but we don't have any good structure to describe the remaining. Right. So how do we make a more more meaningful definitions? How do we study this kind of property? For that, we use this definition. So we say, so a simple graph G is perfect if for every induced subgraph H of G, the chromatic number of G is equal to the chromatic number of H is equal to the clique number of H. Then such a graph is called perfect. And I will show you many examples of perfect graphs. So what are the examples? Okay, so the first example is simple bipartite graphs. Right? Now, every induced subgraph of simple bipartite graph is simple bipartite, so it's enough to prove that chromatic number is equal to the clique number for simple bipartite graphs in order to prove that this graph is perfect. So, what is the clique number and chromatic number? Chromatic number is 2 if it has at least one edge and one otherwise. So most of the time chromatic number is 2, right? Because bipartite graph without edges have chromatic number 1, but otherwise chromatic number 2. Clique number is 2 or 1 if it has an edge and otherwise. So in both cases, chromatic number is equal to the clique number. So that's an easy case, right? Bipartite graphs are easy and we can do many things. Now, the next example is more so interesting, line graph of a bipartite graph. So it's L of G. What is the chromatic number of the line graph? Well, it's chromatic number. And that's equal to the maximum degree by Koenig's theorem. And if you have maximum degree delta, then what can you say? If you have vertex of degree delta, then in the line graph, they become a clique. So you have a clique of size delta. Then omega is the maximum size of a clique, so we get this inequality. So chromatic number is at most clique number. But we have seen that chromatic number is at least, right? We knew already that this is at least clique number. So everything is equal. Right? So for the line graph of bipartite graph, we have equality. How about the induced subgraph of line graph of bipartite graph? Induced subgraph of line graph of bipartite graph is a line graph of some bipartite graph anyway, right? Because deleting a vertex from line graph is same as deleting edges of the bipartite graph. And again, those are the line graphs of bipartite graph, so anyway, it's still equal. So that's the second example. How about third example? So this is complement of the line graph of a bipartite graph. Complement of line graph of bipartite graph. How is that? Right. So what is the chromatic number of the line graph? Right. What is it? It is, we are trying to partition the vertices of the line graph in such a way that each part is a clique, right? So it's a minimum k such that vertices of the line graph can be partitioned into k cliques, right? That's a minimum k. Now it's at least tau of g. So what is this? This is the minimum k such that g has k vertices meeting all edges. Right? If you have a k vertices meeting every edge, then you can, in the line graph, those k vertices will form k cliques, which covers every vertex. Right? So that's a lower bound, right? Because you might have a clique which is not coming from this star from a vertex. So for instance, triangle, right? If this is a graph, then in the line graph they form a clique, but initially it was not like this. But anyway, it's bipartite graphs, we don't have to worry too much. But for so far, for this proof, I didn't even use that fact, right? I'm depending on the inequality. And this inequality is trivially true. So the chromatic number of the complement of the line graph of a bipartite graph is at least the size of minimum size of a vertex set meeting every edge. Now what about the clique number of the line graph G? What is a clique? It's actually maximum size of a stable set. In the line graph, right? What is the maximum size of stable set in the line graph? But stable set in the line graph is like set of vertices pairwise non-adjacent in the line graph is same as matching. Maximum size of a matching in G. So that's a nu, right? So what does that mean? We knew that nu is equal to tau. This is by Koenig's theorem. Because the graph is bipartite, nu is equal to tau. So that means, this means that this is at least chromatic number of the complement of line graph. So this means, again, this is at least clique number, so they are all equal. Okay? And the induced subgraph of the complement of the line graph of the bipartite graph is again complement of the line graph of another bipartite graph. And therefore this already is enough to prove that the line graph, the complement of the line graph of the bipartite graph is perfect. Now there's another example. Complement of a simple bipartite graph. What is that? What is the chromatic number? Chromatic number of the complement of a bipartite graph. So this becomes a clique, right? When you take a complement. So, and you might have a few edges. How do we color that? So when you color this graph, you cannot use two vertices from same part to have the same color. Right? You can. These two vertices are adjacent, so they can never have the same color. So each color class, so when you pick one color, the set of vertices having that color is either have size 1 or 2. Right? So let me say this way, each color class has size 1 or 2. So some color class has size 2, right? And then it has to use the edge crossing. And other color classes of size 1. And when you use the edge crossing, then that's actually edge in the original graph, right? So color class of size 2 correspond to the matching of G, right? If you had an edge in G, then in the complement you don't have an edge, so you can put the same color. So that means the chromatic number of complement of a simple bipartite graph is equal to number of vertices of graph G minus size of maximum matching, right? If you don't have, right, so what this means is you first color every vertex by all distinct colors, and then take a maximum matching. Whenever you have a same maximum match, whenever you have a edge in the maximum matching, then you put both ends to have the same color. So the number of savings you make is size of matching. So it's the number of vertices minus nu. And what is the omega of the complement of simple bipartite graph? This is sometimes called alpha of G. So this is the maximum size of a stable set. Okay? And right, am I cheating here? No, so far. Yes, everything looks okay. So it turns out that there's a nice lemma saying the nu right, alpha G plus tau of G is equal to number of vertices unless G has isolated vertices. Why do I care about isolated vertices? Right. So if I do have isolated vertex, this isolated vertex doesn't contribute anything to tau. Right. So for instance, K1, tau is 0, alpha is 1. Oops. Oh, is it okay? So in this k1 plus k2, in this graph, alpha is 2 and tau is maybe it's okay. Okay, let me put back. Right. So here, why did I write it? The reason why I wrote this is because by conic, we knew that tau of g is equal to nu of g if g is bipartite. So it's enough to prove these equations. So here's a proof. Right. So if tau of g is k, then if tau of g is k, that means you have a k vertices meeting every edge. No, that means you have k vertices meeting every edge. Then when you look at the complement, then g, the complement is size vg minus k. Complement is a stable set because you don't have any edges inside. G has a stable set of size vg minus k, so alpha of g is at least vg minus k. That's one direction. So this means that tau of alpha g plus tau is at least k number of vertices. Conversely, if alpha of g is m, let's say, so you have m, but so this is stable set. Then look at the complement. This is vg minus m. Okay, all edges should be here or there. So this covers everybody, right? So tau of g is at most, and tau is the minimum size of set hitting every edge, so it's the number of vertices minus m. So this means alpha plus tau is at most m, at most number of vertices. Okay, so this proves that alpha g plus tau of g is equal to number of vertices in general. Alright, so that proves this line. So that means tau is equal to nu, so alpha plus nu is equal to number of vertices, and alpha plus nu is the number of vertices. Therefore, the chromatic number of the complement of simple bipartite graph is equal to the clique number. So those are perfect. Okay, and so these are all natural examples. What's funny is we have these pairs of examples, right? When you look at the example 2 and 3, 3 is the complement of the second example, and 4 is the complement of the first example. And that's where this conjecture, weak perfect graph conjecture, okay, this proves that this conjecture that if graph is perfect, then the complement is perfect. Okay, this was all conjectured by who was it? Yeah, Beige. Many years ago. I guess it's 60s. Yeah, 1960s probably. And then there's a strong perfect graph conjecture. which actually implies the weak version. Strong perfect graph conjecture says that G is perfect if and only if G has no hole and no odd hole and no odd antihole. Okay. So odd hole is induced cycle of odd lengths. Okay, let me just say C5, C6, induced C5, C7, C9, That's odd hole. Odd antihole is induced their complement C5, C7, C9. But actually C5 complement is the same as C5. It's isomorphic. Right? Because this is same as so in other words, G has no induced subgraph in C. In this list. Why are they non-perfect? Because when you look at the Cm plus 1, the chromatic number is 3 and the clique number is 2. This is not perfect. What about the complement? When you look at the complement of the C2n plus 1, then adjacent vertices cannot have same color in the complement. So only the consecutive vertices will have the same color. But since you have an odd number of vertices, the number of colors you need is n plus 1. And what is clique? I take every other vertex, so it's n. So these are not perfect. And the strong perfect graph conjecture states that graph is perfect if and only if you don't have these canonical examples. Okay, now both of them are theorems now. Weak perfect graph conjecture has been proved in 1972 by Lovász, and strong perfect graph conjecture has been proved in 2006 by Chudnovsky, Robertson, Seymour, and Thomas. So that's when I was at Princeton, and poor Seymour was very busy working on this conjecture with Maria Chudnovsky, and Neil Lovász and Robin Thomas were visiting Princeton in 2000. So they were really working hard to prove this. So in the next lecture, I will describe the proof of the weak perfect graph conjecture. We're not going to be able to prove the strong perfect graph conjecture because the strong perfect graph conjecture, so it's solved by Chudnovsky, Seymour, Robertson's Seymour Thomas in 2006, and the paper was published in Annals of Mathematics, and the length is like 179 pages. Whereas weak perfect graph conjecture was solved by Lovász in 1972. Okay, so now we knew a lot about perfect graphs. One reason why perfect graphs are interesting is that if G is perfect, then it's trivially, this is true, right? But there is an algorithm. There is a polynomial time algorithm to compute some function. Let's say f. So there is some function. It's called the Lovász zeta function. But if you apply Lovász zeta function to the complement of the graph, okay, so let me say it's a Lovász zeta function of the complement of graph. Anyway, it's not important for us, but this function has a property that it's between the Killing number and the chromatic number. So there is an efficient algorithm so this is due to Lovász. I mean, this function is due to Lovász, but this algorithm is not due to Lovász. I mean, it's three people. GLS. Yeah, so. And Lovász and Schreiber. I think it's in 80s. So they had an efficient algorithm to compute the value of this function. And this function was defined by Lovász earlier, and it's always between chromatic number and Killing number. Now, for perfect graph, chromatic number and okay, what did I say here? It's equal. For perfect graph, chromatic number is equal to the Killing number. So if you can compute this function sandwiched by chromatic number and Killing number, then you can always compute the chromatic number efficiently. So the corollary of this is there is a polynomial time algorithm to compute chromatic number and Killing number for perfect graphs. So that's useful, right? So when you have a perfect graphs, you can always compute chromatic number and Killing number efficiently. Okay. All right. So that's the remark. So, all right. So in the next lecture, we will talk about the proof of the Lovász's weak perfect graph conjecture.